Welcome to Mastering Solutions. Let's start this question again by drawing a picture so we can make sense of everything that's happening. So in this case, for the mourning doves, they say that this keratin layer is surrounded by air on both sides. So we have air on top, air below it, and the index of refraction, as always, is 1. And then here we have the keratin layer, and they tell us that the index of refraction for that is 1.56. So if we draw our wavelengths of light coming through, we'll get some reflection. And then we have low to high. So here is a phase shift. And then some of that will be reflected. And then we have high to low. So there will be no phase shift here. So they want to know what wavelength or wavelengths would this structure produce constructive interference. So we have one phase change and we want constructive interference for this. So the equation for that is going to be 2t is equal to m plus 1/2 times lambda over n. And now we're trying to solve for the wavelengths again. We've done this on several of the previous problems, but let's go ahead and solve it again. We'll multiply both sides of the equation by n. So we have 2tn equals m plus 1/2 times lambda. And now we'll divide both sides of the equation by the m plus 1/2. And so let's write it up here. So lambda is going to be equal to 2tn divided by m plus 1/2. Oops. 1/2. There we are. Okay, so this is the equation that we'll be using. Now, they want us to figure out what wavelengths are going to be produced for this constructive interference. And we don't know what m's to use, so let's just go through and do all of them. So we'll start, and when I say all, we're just going to do several. There's quite a few that you could do. And so m for 0 will have lambda is equal to 2 times t in the thickness, they tell us is 330 nanometers, times the n, and in this case we said it's 1.56 for the keratin, and all that will be divided by m plus 1/2. So in this case, it's 0 plus 1/2, so just a half. Now, we did this on the last question where we didn't really know exactly how many m orders that we should do. So let's do 1, 2, and m3. We can do more if we need, but let's start there and see how that takes us. Okay, so here are all our equations written out, and now we can go through in the calculator and go through these fairly quickly. So let's start off with the first one. We have 2 times the t, which we said in this case was 330 nanometers. And then we're going to multiply that by the index of refraction, which is 1.56 in this case. And now we'll be dividing that by the m, which in this case is 0.5. So that gives us 2059, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, so 2059 nanometers. And so that is going to be like a X-ray level, but 2059 is the M0 wavelength. And then let's go through the others. So we're going to have M for 1 in this case, and now we'll have 1.5. And that's going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, so 686 nanometers. And they don't ask for it, but that's in the visible spectrum, which is going to be like a red color. And so we have red. And then let's do 2. So we have M of 2. And that's going to give us 412. So 412 nanometers. And that's going to be like a purple, kind of like a violet color. Violet, kind of in the blue range. And then let's do one more, the M of 3. So we're going to have 3.5 on the bottom. And so we have 294 nanometers, 294 nanometers. And that's out of the visible spectrum now. And that's like a UV range wavelength. And so these are some of the wavelengths that will get produced in the situation. They didn't ask for it in the question. I'm wondering if they're assuming what visible wavelengths will be produced in this situation. If that's the case, then it's going to be red and violet. If they ask for all, we could go on M3, 4, 5, 6, 7 on and have a ton of different constructive interference wavelengths. So this is the process of how you do it. Look to your question specifically to know what they ask for, if they ask for visible light or the first 4 or whatever they ask for. But that's the answer to this question.